Hello students, in session 1 of thermal methods of analysis, we have talked about a technique TGA, that is thermogravimetric analysis. I believe you remember that in this technique we monitored change in weight with temperature or time, and we got information about the decomposition of a compound. Now, today we will talk about another technique based on thermal methods, which is called as DTA, that is differential thermal analysis. Now, the outline of the lecture will be the introduction, the types of DTA curves which we get, the factors that affect DTA curves. Then I will talk about the difference between TGA and DTA, and finally we will talk about applications of DTA. Differential thermal analysis is a technique in which the difference in temperature between a substance and a reference material is measured as a function of temperature, while the substance and reference material are subjected to a controlled temperature program. In DTA, both the test sample and an inert reference material, say alumina, are subjected to controlled heating or cooling programming. If temperature difference between the sample and reference material is 0, sample does not undergo any chemical or physical change. If any reaction takes place in the sample, the temperature difference, normally represented as delta T, will occur between the sample and reference material. In an endothermic change, such as melting or dehydration of the sample, the temperature of the sample is lower than that of the reference material, which means delta T will be negative for endothermic process. In an exothermic change or process, the sample temperature is higher than that of the reference material, which means delta T will be positive, and we call it as exothermic process. Let us now look at a DTA curve. Here delta T is equal to Ts minus Tr, where Ts is the temperature of sample and Tr is the temperature of reference. Here you can see that the curve is almost horizontal, constant. DTA signal is showing 0 value, and in the case of endothermic change, we see a lower dip in the curve. Again, if it is exothermic, it undergoes upward change and we see a curve like this. This is on the x axis, we have a furnace temperature, and on y axis we are plotting DTA signal. When the delta T value is negative, it is endothermic. When delta T value is positive, it is exothermic change. Here we are writing delta T is also equal to delta H, that is qualitative, where Ts, as I told you, is temperature of sample and Tr is temperature of reference. The shape and the size of the peak gives us an idea about the nature of the test sample. Sharp endothermic peaks indicate phase changes such as melting, fusion, etc., transition from one crystalline form to another crystalline form. On the other hand, the broad endothermic peaks are obtained generally from dehydration reactions. Chemical reactions, the oxidative reactions and physical changes lead to exothermic reactions. Let us consider a block diagram of DTA instrument. Here, this square or you can say rectangle is furnace, where we have two places in which we keep reference and sample material, and this is for the programming for heating or cooling. Now, these reference and sample, they are directly connected to an amplifier and goes to a recorder, and the difference between the two temperature is measured by recorder as delta T. Let us now come to instrumentation part. The DTA apparatus consists of the following components. First, furnace sample and reference holder with thermocouple assembly. Second, sample holder furnace, as we have already seen. Third, furnace temperature controller to increase the furnace temperature steadily. Then, furnace atmospheric control system to maintain a suitable atmosphere in the furnace and sample holder. Then, a recording device which can measure the temperature of reference material and the substance under investigation, so that we directly get the value of delta T. Let us now come to the first part, furnace. It is designed in such a way so as to incorporate an appropriate smooth input, thereby maintaining either a fixed temperature or linear heating program. Normally, we use close to 5 or 6 degree Celsius per minute increase in temperature. Temperature is controlled via a thermocouple which is attached to the furnace. For different maximum temperatures, different thermocouples are used. For example, if we want to go to 1100 degree temperature, we can use nickel chrome as thermocouple. If we wish to go to slightly higher temperature like 1450, we can use platinum rhodium thermocouple. For still higher temperature, we can use graphite tube furnace, which permits temperature greater than 1500 degrees Celsius. Then the sample holder. Both metallic and non-metallic materials are used for the fabrication of sample holder. Metallic materials generally include nickel, stainless steel, platinum and its alloys. Non-metallic materials which are used generally include glass, silica, alumina, etc. In metallic holders, sharp exothermic and flat endothermic peaks are observed. In case of non-metallic holders, relatively sharp endothermic peaks and flat exothermic peaks are observed. These are some substance holders. You can see these are metallic one and these are non-metallic one, which are used for DTA analysis. temperature controller. In order to control the temperature, three basic elements are required. First, sensors, second, control element, and third, heater. On-off control. If the sensor signal indicates that the temperature has become greater than the set point, this is not used in DTA. Proportional control. These controllers are used to set the temperature. In thermoanalysis, the signals obtained by the sensors are recorded, then the signal trace is produced on the paper or screen or sometimes even on films. For example, nowadays generally a monitor is used to monitor the DTA plot. Let us consider an example for DTA of calcium oxalate monohydrate. The thermogram shows the decomposition in CO2 atmosphere as well as in air atmosphere. Just see here, this is a normal thermogram which we get for DTA curve. On x axis you can see it is temperature starting from 0 to 1000 degree, and on y axis it is the value of delta T in percentage per minute. You can see here, in contrast to TGA where we were getting steps, we get peaks, and here you can see the first peak is around 180 degrees Celsius, which indicates about 12.57% of water. Then let us now come to the second one, which is very close to about 430 and indicates 19.47% carbon monoxide, and the third one is close to 640 and shows about 30.07% carbon dioxide. And therefore, you can see that in DTA we are getting peaks in contrast to TGA where we were getting steps. The heating rate plays an important role. For example, here you can see that if heating rate is too fast, we get the last peak at 431.2 degree Celsius. Here the first one is at a heating rate of about 1 degree per minute, whereas the second, third and fourth they are at 5, 10 and 20 degrees Celsius per minute, and you can see that the temperature which we are observing is also dependent on the heating rate. However, for getting good results, we should not use a very fast heating rate. Here you see the thermograms which we got for decomposition of calcium oxalate in air as well as in carbon dioxide atmosphere. Here you can see that in the first case in air we get an endothermic peak followed by exothermic peak, and the third peak at around 800 degree, which is also endothermic in nature. Whereas, when we use carbon dioxide atmosphere, we see that all the three peaks are endothermic in nature. The DTA curves of calcium oxalate monohydrate in air and in carbon dioxide environment show the successive elimination of water, carbon monoxide and carbon dioxide. Three peaks or points in carbon dioxide environment of weight loss corresponds to endothermic process. In air, three peaks represent the weight loss, in which second peak represents sharp exothermic process, but it corresponds to the same weight loss as in carbon dioxide atmosphere. This peak represents the exothermic burning of carbon monoxide in air at the temperature of the furnace. Here, let us now see what is actually happening. This is the temperature starting from 0 to 900 degree, and here we are considering 0 exothermic process and then downwards endothermic process. In the first step, which is endothermic process, we can see that calcium oxalate monohydrate is giving calcium oxalate plus water molecule, that is, the removal of water takes place at about 220 degree Celsius. The second peak, which is exothermic in nature, shows the reaction calcium oxalate reacts with oxygen to give calcium carbonate, and 2 molecules of carbon dioxide are eliminated. Whereas, in the third step we can see, which is again endothermic process, calcium carbonate gives calcium oxide and carbon dioxide is eliminated. DTA is a dynamic temperature technique, hence 2 types of factors can affect DTA curves. First, instrumental factors, that is, size and shape of the sample and furnace holder affects the nature of DTA curves. Second, material from which sample holder is made and its corrosive nature also affects DTA curve. Then, wire and bead size of thermocouple junction affects DTA curves. Heating rate, as I already told you, also affects DTA curves. Speed and response of recording instruments and thermocouple location affects DTA curves. The sample factors, amount of the sample, that is, the weight of the sample which we have taken, also affects DTA curve. The particle size of the sample, thermal conductivity of the sample, heat capacity of the sample also affects DTA curves. The packing density of the sample, effect of diluent which is used, degree of crystallinity also affects the DTA curves. The value of delta T determined by DTA is not very accurate. Always an error of 2 to 3 degrees Celsius is a common error which we frequently see. A small change in delta T cannot be determined and quantified. Due to the heat variation between the sample and reference, the technique is less sensitive. Let us now come to applications of DTA. DTA curves for 2 substances are not identical. Hence, they serve as a fingerprints for various substances. It is used to study the characteristic of polymeric material. DTA is used in the ceramics and metal industries. The technique is capable of studying high temperature processes. An important use of DTA is for the generation of phase diagrams and the study of phase transitions. DTA method also provides a simple and accurate way of determining the melting, boiling and decomposition points of organic compounds. Trained in ligand stability, that is, thermal stability of various ligands, gives the information about the ligands in the coordination sphere. Let us now consider application in food industries. The correct combination of the gum formulation can be determined like elastomers, glycerine, softening agents and carbonates, flavoring agents, polyvinyl acetate can be determined by using DTA. Let us consider an example of double mint chewing gum sample. Here you can see the red curve represents the mass loss. Here you can see up to certain temperature the mass loss is insignificant, and then a sharp increase in mass change occurs with increase in temperature. Whereas in DTA sample, here we can see the sharp peaks which are endothermic in nature, and you can see the second peak, a third bump, fourth peak, and this indicates that if we heat it at 20 degree C per minute, that is 20 degrees Celsius per minute, we can see the results for thermal analysis of this chewing gum. Let us now consider another application of DTA in the study of phase transition of sulfur. Now, sulfur exists in various forms. At 124 degree, the sulfur melts and it is the melting point of sulfur. At 113 degree, the rhombohedral sulfur changes to another sulfur which is monoclinic sulfur. So, the phase is transferred from rhombohedral to monoclinic. At 179 degree, it changes to liquid phase transition, whereas at 446 degrees Celsius, it starts boiling and it is the boiling point of sulfur. By using DTA, we can see how this curve look like. On x axis, we have temperature. Here on y axis, we are using delta T, and here we have endothermic and exothermic processes. Here we can see that at 108 degree, the peak begins and we get a sharp peak at 113 degree Celsius, whereas the second peak appears at 124 degree Celsius. The third peak, which begins at 172 degree Celsius, gives a sharp peak at 179, whereas the last peak appears at 446 degree Celsius. Now, all these temperature indicates the change in phase transition of sulfur. To summarize, we have learned in session 1 and session 2 of thermal methods of analysis, we have learned TGA and DTA techniques. As you must remember that in TGA we got stepwise changes when we monitor change in weight with change in temperature or time, and in DTA we monitor the value of delta T, which also indicates exothermic and endothermic nature of the changes, and we monitor it with change in temperature. In DTA, in contrast to stepwise changes, we get sharp peaks. We learned about the instrumentation of DTA and TGA, the nature of curves in both the cases, and then the application in the industries. In the next lecture, we will talk about a couple of more techniques which are based on thermal methods, but they are different than DTA and TGA.